Hello, in this presentation I am going to present about the stellar nurseries, star evolution and something about galaxy. So first we are looking on a stellar nursery which its name is Orion. We know this Orion cloud is most familiar for us. We know Orion Nebula. Most of us had seen this Orion Nebula. It is near to the belt of that Orion constellation. So this is the this is the portion of Orion Nebula. Actually, this Orion Nebula is a part of Orion molecular cloud complex. This region is called Orion B cloud, and this region is called Orion A cloud. These are the major portion of this Orion molecular cloud complex. We will tell about this Orion Nebula later. So the mass of major component of this Orion molecular cloud complex is hydrogen molecules, and its mass is around 10 raised to 5 solar mass, and the other components are carbon monoxide, ammonia, dust grains. These dust grains will make dark clouds. Dark clouds means we cannot see visible light from that, so that's why it is called dark clouds. So this is the map of this Orion cloud complex. We can see dark clouds in this map. And this is the map of 2.6 millimeter line of carbon monoxide, especially carbon 1216O, which is carbon isotope of this carbon. Later we will see the line 2.7 millimeter line of carbon 13 or 16. So that's why I specifically say the mass number of carbon here. So this is the map of 2.6 millimeter line. We can see Orion A and Orion B. Why do we use carbon monoxide to map? Because we are using this carbon rotational, this 2.6 millimeter line is the rotational spectra of carbon monoxide. We use this to map the molecular hydrogen. We use 21 centimeter line to map the atomic hydrogen, and 2.6 millimeter line of carbon monoxide to map molecular hydrogen. We use the concept that the abundance of this carbon monoxide and hydrogen molecule is 1:10,000. That means if we detect one carbon monoxide molecule, that means there will be 10,000 around 10,000 hydrogen molecules around that. So that's why we use this. So and the number density of this 2.6 millimeter line is around 10 raised to 3. That's just 10 per 10 molecules per centimeter cube. And this inset is 3.1 millimeter line of carbon sulfide, and this is also this is a dense region. Then this is a major portion of star formation. So this is the picture of Orion Nebula. I took this picture from Stellarium, screenshot of Stellarium software. So here we can see the light in visible region, how this light is forming. In this region there is around 4 O and B type stars, which are the spectral type of star. O and B stars have a very high temperature, which is much higher than our solar temperature. So it can produce the ultraviolet photons, which have energy more than 13.6 electron volt. So this can ionize the hydrogen. Then this region, because of this region is the gas in this region is ionized. But not only ionization, the electron and proton can also recombine again and can emit photon. So we are seeing the photons escape in this way. So this is the Orion Nebula. We are seeing Orion Nebula in that way. And this is the another molecular cloud. Its name is Taurus Auriga, and its position is northeast portion of Orion. We can say that in a large portion we cannot see any kind of stars. We can claim two things: either there is no stars in that region, or there is something which blocks the our vision from the star. So if second claim is right, if we take the map in some other wavelength, maybe 2.6 millimeter line, or in some infrared wavelength, that means there should be dust particles, or if we take 2.6 millimeter line, there should be carbon monoxide. If we take 21 centimeter line, that will be carbon atoms. So if we take such kind of maps, there should be something. If we do not see anything in those wavelengths also, we can say that there is no there is no stars in this region. But when we took this 2.6 millimeter line, we could see that there is dark cloud, there is clouds in that region. So mainly that is dark clouds. That means the visible light from the stars behind that is absorbed by the dust particles in this cloud. That's why we cannot see visible region, but we can see infrared in that region. So next is the map of this molecular hydrogen in this region is around 10⁴ solar mass. So this is also a stellar nursery, that means a major portion of star formation. This is the 2.7 millimeter line of carbon isotope, carbon monoxide, that means 13 carbon 16 isotope. This is also a carbon dioxide, carbon monoxide map of the central region, and yeah. So here is the dense map of dense core. It is mapped by 1.3 centimeter line of ammonia NH3. So when we detect ammonia map, that means that is a dense core. In dense core, the gas is almost cold, so we cannot see much rotation spectra of this carbon monoxide, but we can see this ammonia map, ammonia spectral lines. That's why we use ammonia to map this dense core. So next we are moving on to analysis of star evolution. So to the analysis of star evolution, we take two quantities mainly. Those are luminosity and effective temperature. Luminosity is mainly the intensity of star coming from intensity of star, and effective temperature is we are calculating it theoretically from the spectra. We are thinking that the star is a black body, then we take the spectra of that, then we fit with the theoretical value. In that way we are taking the effective temperature, and capital M is called absolute magnitude. So in earlier days people are observing these stars in naked eye, and eye can detect the change in this intensity in logarithmic scale. That's why we use logarithmic a logarithmic quantity. So this absolute magnitude means the that thing is called a magnitude, that quantity is called a magnitude. So this capital M means this magnitude of star in 10 parsec, and this small m means the magnitude of the same star in some arbitrary distance. We use this capital M lambda for as our convention to make it in 10 parsec. So when we think about it, we take this mv something proportional to log of this f, which is the flux. Then we know that the flux is dependent on 1 by r square, then we replace 1 by r square there, Then after some rearrangement, if the r square r is 10 parsec, we get capital M. If some other value, we will get this thing plus this plus some other quantity. So that will be small m lambda. Lambda is the wavelength. These are the wavelength dependent quantities. Then this V and B are some particular wavelength we use as standard bands we use. So this quantity is called intrinsic color index. This is just yeah, this B is a particular wavelength, V is also a particular wavelength. I don't remember the values of that. So we take this difference and we call it intrinsic color index. And HR diagram is the map between this absolute magnitude and this color index. Now we define it like this. Later we will replace it with the logarithm of effective temperature and luminosity, because those quantities are dependent on these things. So that is more easy for us. That's why we use that. So in this region is the this is the region of main sequence. Main sequence stars are seen in this region. This is the position of our sun. So now let's look on the evolution of star. So in the pre-main sequence, means after the birth, the stars are born in this region. That means the cloud molecules in clouds are coming together under gravity and it starts collapsing. Then the particles will lose its energy because of this gravitational collapse, and it can be transformed to thermal energy. Then the temperature of that region can increase. So that's we are seeing that thing. First its luminosity is decreasing, that means it is becoming dense. Then the temperature is increasing, that means it is losing its gravitational energy. Then at some point of time the hydrogen nuclear fusion is starting, that means the it joined to the main sequence. After some years, some millions of years, it joined to the main sequence. All these are happening in the time scale of millions of years, not a certain process. So then it is joined to the main sequence. This ZAMS means zero age main sequence. Then it joined to the main sequence, that means the nuclear fusion is happening at the core of the star. It is continuing. When it joined to the main sequence, then the star reaches the equilibrium condition. Then the energy production is continuing at the core, and thus that energy will reach to the surface of the star and it will radiate away. Then after if the hydrogen fusion is almost complete, that means the fuel is almost complete, then it starts it moves to this region, means without further changing in the effective temperature, it start expanding, because the radiation pressure is there, and it's I shall draw the picture. So if this is a star and this is the core, in the core the hydrogen nucleus is almost finished. That means there is no further hydrogen nucleus to happen the nuclear fusion. But still in the outer regions there will be hydrogen nucleus. So there can have more and more, there can continue the nuclear fusion. So there nuclear fusion happens, and the energy is producing that can push out this region, but more helium can be added to the core, and the core is expanding, but the pressure is increasing. Then the outer layer starts expanding. So that's why the luminosity is increasing. So at that portion we call it red giant. Then after a long time, the outer layer will become go away. Then, but if there get again the sufficient temperature to this helium nucleus, the nuclear fusion starts again. Then this process continue and form some heavy metals. That means heavier nucleus. But the same thing can repeat again and again until it reaches no further temperature to happen this nuclear fusion. Then it move to the phase of planetary nebula, then white dwarf. We know all these things, so I do not explain it here. So these are the things I mentioned earlier. See, the effective temperature of life of a star is around 10 raised to 7 years. So these are the birth line and main sequence region. These are the different ways to reach from birth line to main sequence. So the entire fate of the star is decided by the initial mass. Each mass will follow each line. So now let's move on to the galaxy, galactic context, which means our solar system is around 8.5 kiloparsec from our galactic center. In this region, the solar system is moving in around 220 kilometer per second around the galactic center. That means the solar system is also revolving the galactic center, and the position of the solar system is in the galactic disk, and the time period of this rotation is around 2.4 into 10 raised to 8 years. Then you can calculate after the birth of sun how much time, how many times it completed the revolutions, how many revolutions have completed. Then the average vertical thickness of the disk is around for O and P type stars it is around 100 parsec. You mean the O and P are the spectral type, that is heavier mass at a high temperature, and G type star is around 350 parsec. So O and P type is more congested to the disk, and more stars are concentrated in the central bulge, which have the radius around 3 kiloparsec, and the more distance from the central disk there will be globular clusters, mean the star clusters, and field stars. Field stars means the stars which do not belong to any globular clusters. Our sun is a globular is a field star. It does not belong to any globular cluster, and there will be a lot of interstellar dust, other gas particles are there, and this dust will diminish the light from the distant star. We have seen in the case of Taurus Auriga, we couldn't see a lot of stars in that region, so that's mentioned here. So early type galaxies means the galaxies which have aged more than the age of solar system was forming mainly in elliptical region. So our galaxy, which is Milky Way, is a spiral galaxy. So in spiral galaxy there is spiral arms. So there is a theory called density wave theory, which says the arm in the spiral galaxy is actually a density wave which is moving. When this density wave comes, more stars will form in that region, then it will go away, the star formation will decrease, rate of star formation will be decreased. And one thing is, the more massive stars are concentrated in spiral arms. Remind one thing, the life of a typical star is 10 raised to 6 years, and it is only 1% of time period of a spiral arm. So this is a map of a spiral galaxy, And next is we had seen that the stars are forming this interstellar matter. Interstellar means between the stars. Stars are forming from this interstellar medium, interstellar gas. So, what is happening if a star dies? The, the stars formed from this interstellar dust. Then, after the processing, means heavy metals are formed by nuclear fusion. Then the same thing will move to the interstellar dust by supernova, by the expansion of this red giant, etc. That will also contribute to the interstellar medium. So that's all about this presentation. Thanks.